We'll take a look at this HL example. I'm calling it double whammy, and this is a very common trick that IB plays with us. So we've got an arithmetic sequence as U1, U2, U3 has U1 equal to 1, and a common difference is not equal to 0. So now the values U2, U3, and U6 form the secondary sequence that is a geometric sequence, and so that's why I'm calling it double whammy. Goal is to find the value of D and then to evaluate the value of this symbol here. Start with part A and try to make sense of this information here. So we have U1, U2, U3, U4. So this is 1, 5, U6, UN is negative 15. Okay, so U1, U2, U3. Now, if we take U2, U3, and U6, they form another pattern that's geometric. And it looks like we really have very little go on here. And so what we're going to do is represent these with placeholders. So in an arithmetic sequence, this would add by a common difference, which is not 0. And so the second value in the sequence would be the 1 plus whatever the difference is. And then the next one would be 1 plus 2 differences, 3, 4, and then this would be 1 plus 5 differences. So we're going to take those as placeholders representing those values in that arithmetic sequence, and we're going to form a geometric sequence out of those. So in the geometric sequence, this is sequence, it's going to be, I'll give it, say it's A1, A2, and A3. I'll give it different lettering here. So that'll be the geometric one. And the first value is 1 plus D. Second is 1 plus 2D, 1 plus 5D. Again, doesn't look like there's much to do here, but we're going to figure out what the ratio is here. There's a ratio between any two consecutive pairs here. I'll just give you an example, like what about 2, 10, and 50? That's geometric. If you were to take 10 over 2, that makes the ratio 5, and that ratio is preserved if we take the next consecutive pair and do the same thing. So those two are equal, and we're going to use that with this algebraic statement to figure out D. Setting it up here, that would look like 1 plus 2D, 1 plus D. That's the ratio between this consecutive pair, and then that's got to be equal to the ratio between the next consecutive pair. All right, so there's the setup, solve for D. And I don't like the fraction nature of this, so I'm going to multiply both sides by, let's switch colors here, 1 plus D. And doing so here will cancel out that factor and leave the 1 plus 2D alone by itself. And then we still have 1 plus 2D in the denominator here. So I'm going to do these two steps at once. I'm going to also multiply both sides by the denominator here. Keep it balanced. So we're going to do it to both sides, 1 plus 2D. Looks a little bit sort of confusing, so let me just clean up what that reads as, and I'll stick to the black. It'll read 1 plus 2D, 1 plus 2D, 1 plus 5D, 1 plus D, solve for D. And then we're going to box method the two of these here and combine like terms, see what we get. So this is going to be 1 plus 4D plus 4D squared. And this will be 1 plus 5D, 6D plus 5D squared. It looks like we have a quadratic on both sides. And with quadratics, the goal is to get 0 on one side. So if we balance all the parts here, the 1, subtracting that will cancel out. 4Ds will turn into 2Ds, and then the D squareds will be 1D squared. And then how many D? 2Ds. And then no constant value. Solving this, I'm noticing that there's a greatest common factor of D, and so we'll just go ahead and factor that out. D plus 2. Those are mathematically equivalent. Just helps us to solve this. So D is either from this factor, D is either 0 to make this a true statement, which is said in the original statement here. It can't be 0, so that was a decoy answer. Instead, the answer comes from this factor, D equals -2. So that's the difference of the above pattern, meaning that this goes 1, -1, -3, -5, and so on until we get to -15. You probably just count that out if you wanted to. But we are going to need to know, well, what spot in the sequence is this -15? And we can do that a little bit quicker than just making a table, although that's not, won't take too long to do that. But the sequence equation, arithmetic sequences, goes as such. And so we'll plug our information in here. -15 equals 1 minus 2 and minus 1. Solve for n. -16 minus 1, 8 minus 1, and then 9. Okay, so it turns out this is the 9th value in the sequence, -15 is. You could have figured that out just by carrying on the pattern, but that's going to become important when we evaluate this part B. Determine the value of this sum. This sigma notation represents the sum up to, we just figured out, the 9th value of the UR. Like, I guess I was using n's. N is a very special R in the way they've written this out. So in here, the R is the variable, and then N is a specific value of R representing the last value that we're concerned with, which happens to be the 9th value. So that's what all that sort of crisscrossing of the variables means. I'm going to switch over to here, and then we just figured out this was the 9th value. And so to reiterate here what this means to do this summation, we're just going to add 1 plus, next one was -1 plus -3 plus ... -15 will be the 9th value. So this sigma notation just means to add up all those terms. And if it was a calculator problem, we could just, well, you need an equation for this. So the way it's set up here leads us towards a non-calculator approach. And the non-calculator, or the equation for arithmetic sequences, which is the sum of a series, there's 2 of them. The one I think is going to be quicker in this case goes as follows here. It's going to be the number of terms divided by 2 times the first plus the last pair. And so this is going to be 9 terms over 2, S9. The ninth sum of the first 9 terms is 9 over 2, 1 plus -15. And we'll just go ahead and evaluate that. So S9 is 4.5, -14. And let's doing this non-calculator here. Do this -10 minus 4. That's going to be easier. So it's going to be -45 and a negative, let's see, 18. Just doing some mental math there. That's a 45. So I essentially distributed this. Okay, and then that's 50, 63. So this symbol represents the sum equivalent to -63, which is the sum of all those terms in the sequence. Okay, so we had a double whammy here. It's a very common thing to do in IB, where you start with the arithmetic sequence, and then you've got like a sub-sequence within the sequence that happens to be geometric, and you have to use this idea of common ratio, or I guess it could have been the other way around, whereby you start with the geometric, and then so there's variation on theme.